All right, good afternoon or good morning, everyone. Welcome to this week's Green Bank Observatory Community Zoom. I have just a quick announcement or two before we begin the talk. The good news is that the Green Bank Telescope will finally be back on the air starting tonight. It's been a long slog getting back to operations. We had some damaged wheel. We had some foundation work that we needed to take care of. And after a hibernation of a couple months, getting back into operations, there were a couple hiccups on the way. There was a servo control issue that we fixed. And the new wheel is was making some pinging noises that we wanted to make sure that we weren't causing further damage, but we had the experts come out today and take a look. The bearings are fine. We think what's happening is there's a stiction problem with the axle, but that is normal and to be expected. This happened early on in the history of the Green Bank Telescope. So we're ready to begin observations tonight. So check your schedules. If you're on the schedule, you'll be good to go. There is one little bit of a restriction because of this issue with the axle. We want to keep an eye on it, and we don't want to run at full rate, so we'll be limited to half azimuth rate. So the slews may take a little bit longer than you're used to. That's typically what we do in the dead of winter. So please be patient. We're just going to keep an eye on it and just make sure that as the wheel settles in, things get a lot better. But very good news. I want to thank the telescope operations team, the mechanics here, who have done a fabulous job in working through all these infrastructure issues, and I couldn't be prouder of our team. It was a lot of challenges that we faced, and we're eager to take your data again. So good luck with all your new observations, and please let me know how things are going. All right, so just a couple other things. The deadline for the single dish school applications is tomorrow. The school takes place here from August 7th to 11th. So if you're planning to attend the single dish school, you have one more day to apply. And just one last thing, the time allocation committee, the TAC, is meeting here at Green Bank next week. So your proposals will be reviewed, and you'll get your disposition letters in so that is all I have. So I'll hand off to Dave Frere, who will introduce today's speaker.
Hello, everyone. Our speaker today is Dan Stinebring, and he's from Oberlin College, and he'll be talking about the title of his talk is How Porous is the Ionized Interstellar Medium Results from a Scintillation Arc Survey. And just as a reminder, how we do these community Zooms, we ask you to put your questions in the Q&A box, and then we'll take care of them at the end of the talk. And but feel free to ask questions then. Thank you. Go ahead and take it away, Dan. I see you're loading up your presentation now.
Yes, I'm searching for the right presentation. Okay. All right, very good.
Perfect.
Is that full screen now, Dave?
Yes, it is.
Okay, very good. Well, good afternoon or morning, everybody. Thanks so much for the opportunity to share our work. And I'd like to thank the National Science Foundation for supporting this work. And I'd particularly like to thank my collaborators. Tony Minter took almost all of the Green Bank observations that I'm reporting on today, and Barney Rickett was a key help over the last 2 years in finishing this project. So, as you know, depth is always challenging in astronomy, and we are, that's no less true in studying the interstellar medium. But fortunately, we have some tools at our disposal, and the key one is the dispersive nature of the ionized interstellar medium. So this happens to be a pulse from an FRB, from a fast radio burst rather than from a pulsar, but nevertheless, the idea is the same. We see that the high frequency radio waves arrive early, and then the pulse sweeps down in frequency, arriving later at the lower frequencies, and it following a strict 1/frequency squared law. Now, there's also another phenomenon visible in this FRB sweep, namely that you can see brightening of the burst as you go, as it sweeps down in frequency. And this is due to another phenomenon, namely multipath scattering in the inhomogeneous interstellar medium. And the inset in the upper right shows another manifestation of that, or consequence of that, namely the scatter broadening of the pulse, which becomes more pronounced as we move to lower frequency, because the bending power of the ionized ISM becomes much greater at lower frequencies. And so this is the picture that I have in mind, or at least one picture that I have in mind when I'm talking about multipath scattering in the ISM. So we have a pulsar over on the left, we have the telescope over on the right, and we have some inhomogeneous medium that is localized in a fairly small region of space along the line of sight, a fairly small fraction of the line of sight. And this gives rise to an interference pattern at the telescope. And it gives rise to an interference pattern because the angular size of the pulsar is so small that the electric field, we have coherence of the electric field along each one of these paths. And when they recombine it in the vicinity of the telescope, we get an interference pattern in space and also in frequency. And the modulation in space gets converted into a modulation in time because of velocities in the problem, transverse velocities in the problem. So as you know, stars twinkle, but planets don't. And that's because of their angular size coming through the Earth's atmosphere. And similarly, pulsars twinkle in the ionized interstellar medium, whereas quasars don't, because they don't have the incredibly small angular sizes of pulsars, which can approach 10 micro arc seconds or even less, depending on the scattering along the line of sight. I want to show you some results of this survey that we've done, and then I'll tell you a few more details about the survey and wrap up with some conclusions. What have we learned about the distribution of material along the line of sight? So this is one of the 22 pulsars that we looked at in this survey. These are GBT observations. These are the 3 radio frequencies that we used in the program. And you can see these dark patches of higher intensity, higher flux density showing up in these dynamic spectra. And these are linear grayscales, and dark means high flux density. And you see that as we go down in to lower frequencies, we start to, because of the additional bending power in the interstellar medium, the extra path lengths are longer, and also Doppler shifts along the ray path are also larger, and both of those give rise to smaller scintillation maxima, or as we call them, scintils. So down here at 340 megahertz, the scintillation structure is quite small. So I was talking about different tools that we have to explore the distribution of material along the line of sight, and in this case, it's along the line of sight to pulsars. And I talked about dispersion and talked about scattering, but there's an additional tool that we have that that we discovered in 2001, and that is what is called the secondary spectrum. And so in the top panel here, I'm showing a dynamic spectrum. These data happen to be from Arecibo. You can see this rich crisscross kind of pattern that's showing up in this dynamic spectrum. We have about 2,000 frequency channels. Vertically, we have a spectrum from the source every 10 seconds. So we have 360 resolution elements in time. So we have a nice rich image in the upper panel. If you take the two-dimensional power spectrum of that, what we call the secondary spectrum, that is what is shown below. And lo and behold, this rich and complicated pattern up above resolves into something much simpler and highly structured in the secondary spectrum. And furthermore, if we were to take the next hour's worth of data, take a dynamic spectrum just 1 hour later, we would find that the details of the dynamic spectrum were completely different in detail from the first hour. However, the secondary spectrum would be identical. And we have done this many times. Other people have done this many times. This is not a theoretical prediction. This is something that that you can reproduce on your own kitchen table once you have the data. Now, I want to give you a sense of how we can distinguish between scattering dominated by thin screens along the line of sight and scattering that's being caused by a space-filling clumpy medium that is causing the rays to random walk their way from the pulsar to the observer. And that latter picture is over on the left. The thin screen picture is over on the right. And the main point here is that it's only in the diagram on the right, only in this thin screen kind of geometry, that we expect to get a very sharp and well-defined scintillation arc or parabolic structure in the secondary spectrum. If we had the more distributed clumpiness, then in fact what happens is there is no longer a one-to-one relationship between the time delay of a particular ray and the effective Doppler shift along that ray. Whereas on the right-hand case, in the thin screen scattering, there is a one-to-one correspondence, and that is what produces the sharp scintillation arc. So here are some scintillation arcs from our Scintillation Arc Survey, or SAS, and you see them at the 3 different frequencies, and you see that as we go to lower frequency, the arcs get broadened out. What I'm meaning to say there is the arc gets fuzzier, and also the curvature changes. And I want to dwell on that last point. I have just this one slide with a technical detail, because the technical detail is important for how do we go about using the observations to determine the location of the scattering material. And we do that through the curvature of the parabola. So we have a parabolic signature here. Tau is our vertical axis delay. Doppler shift is our horizontal axis, F sub D. The curvature relates the 2 of those. And then down here, you can see the way that the distance to the pulsar, the observing wavelength, and the screen location S, which is just the fractional distance from the pulsar to the telescope, shows up. And then there's one more parameter here, this parameter alpha. And this parameter alpha is the unknown angle between the highly elongated image of the pulsar on the sky and the effective velocity of in the problem as projected, both as projected onto the sky. Now, I'm saying the highly elongated image of the pulsar. Now, in most cases, we do not directly image the pulsar, but we can infer the elongation from other aspects of our observation, and in some cases, including radioastron and some other imaging of pulsars at with VLBI, it's been confirmed that there's oftentimes this elongation from moderate to extreme. And so this angle alpha comes into play. And that's problematic for locating the scattering material, because everything else tends to be known in the problem. But the location S and alpha are then both come into play here in terms of determining the curvature. Now, if we know nothing about alpha, the fact that alpha can't be any smaller than 0 means that we can get a lower limit on the location of the scattering screen in terms of the distance from the Earth. And so that's useful information, but it's also very helpful oftentimes that we can use the Earth's orbital motion around the sun, or in fortuitous cases, and sometimes quite cases that we're very interested in, the binary motion of the pulsar around a white dwarf or a neutron star, to break this degeneracy and to independently determine S and alpha. So we set out to do this survey, and we were interested in the question of how much evidence is there for scattering, distributed scattering along the line of sight as opposed to scattering in the screens, and also how this might relate to, let's say, known structures like the local bubble or other ISM bubbles that are known. And we have 22 pulsars in the survey. These were all small to moderate dispersion measures. Most of these observations were done with a GBT, but 6 of the pulsars, the weaker ones in the sample, were observed at Arecibo. And we specifically chose these the pulsars to have this range in DM. But other than the range in DM, we then only made sure that the flux density was sufficient to give us a good signal, and otherwise we just tried to have a representative sample. We didn't select on any other source criterion. So the next slides just show you the overall quality of the observations and some of the details that we were able to see. So I think I have 5 slides now in a row that are all this same format, 5 different pulsars, all observed with the GBT. And you see at the higher frequencies, we can see multiple scintillation arcs. It gets a little murkier at the mid frequency, and then at the lower frequency, it gets blurred out even more by the increased scattering at the low frequency. And here's another source, and you can see evidence here and in several of the other observations for more than a single parabola. This is like 2 nested parabolas. And by the way, you've probably picked up on the fact that the upper half plane and the lower half plane have the same information in them, because we started off with a real valued function before taking the power spectrum. Another beautiful case, GBT at its finest, this was actually taken with this spectral processor. I wish the higher frequency data use the Vegas spectrometer. Another example with some multiple scintillation arcs. Notice there's one here with very low arc curvature. And so as beautiful as those data are, I want to finish the talk by bringing this up to date a bit. And I mean, we just published these results last year, but there are some new and spectacular results that are coming in from even larger, more sensitive telescopes. And I want to show you 2 slides now from Stella Acker, who's currently at Cornell, but will soon be going to Caltech and Carnegie observatories as a postdoc. And these are data that she obtained with the FAST telescope. And now this pulsar is 1 kiloparsec away, and shows at least 4 scintillation arcs. You can see 2 nested ones in the central region, and then there are 2 fainter ones at even wider curvature, smaller curvature values, which places them closer to the pulsar. Here's another set of observations that she obtained at FAST. In this case, she's able to identify 8 distinct arcs over 360 parsecs. And when I'm saying 8 distinct arcs, in my thinking, that's synonymous with 8 distinct scattering locations along the line of sight, discrete scattering locations, scattering screens along the line of sight. And then one last data slide, and this is taken with the Meerkat telescope. And these are observations and a slide prepared by Daniel Reardon, who's at Swinburne University. And for this pulsar, only 160 parsecs away, he identifies at least 20 scintillation arcs. So that averages out to something like a scattering screen every 8 parsecs on average. So I haven't had time in this short talk to take you through the chain of reasoning involved in all of these conclusions, but I encourage you to read the paper, and or I'm also happy to talk with you more about this. But we found that the scintillation arcs are a ubiquitous phenomenon that was not completely known before the scintillation arc survey, and We think that most of the scattering is coming from physical screens of some sort and discrete places along the line of sight. Very little distributed scattering, relatively speaking, although this is still, it requires more detailed modeling to make that a more quantitative statement. That clumpiness that you saw in one of the early secondary spectra, when you convert that into location on the scattering screen, we're talking about clumpiness on an AU size scale. And then these new results coming out of the even more sensitive observations are indicating that, in fact, whatever these is causing the scattering along the line of sight, it may be occurring as frequently as every 10 to 20 parsecs spacing. So that's clearly exciting stuff to follow up on, and I will leave these up and be happy to answer any questions.
Thank you very much, Dan. That's very interesting. So we're opening up for Q&A. Right now, I don't see anything open up in the box right now, but I'll go. Can you ask a question? I was curious, do you have any constraints on the quote, the thickness of the screen?
That's a good question, Dave. And we do, as a matter of fact. I don't here, let me just I won't try to switch slides or slide deck right now, but well, let me just I may have attached. Oh, I do actually have a slide that will answer this question. So this slide is an old observation, old set of observations, and what we're showing here is we're using the orbital motion of the Earth around the sun to model the location of the scattering screen. And so in terms of fractional distance from the pulsar to the Earth, you see a line for 0.37, 0.38, and 0.39. And you can see then that really it's we're able to basically constrain the thickness to be something like just a few percent of the distance along the line of sight through a technique like this, through an analysis like this.
Okay, thank you. We've had several questions come in now, so I'll just read through in the order in which they came in, or maybe, well, actually, this is the reverse order, the order in which they're showing up on my screen now. The first question: what density contrast do you need to produce these discrete screens, and how are these putative structures consistent or with a scale-free Kolmogorov turbulent? So are the screen, I mean, big picture here in terms of
yeah. So there's really two good questions in there. Let me take up the second one first. And so with regard to the Kolmogorov and the comment about the Kolmogorov, what we're really saying there is that the behavior of the scintillation arcs in detail, particularly as we explored them at the multiple frequencies at nearly the same epochs, behaves as if the medium causing the scattering is consistent with Kolmogorov turbulence. Now, it's not the only model that necessarily works, but it does work, and so that's the comment there. So that's not meant to indicate Kolmogorov turbulence throughout the whole medium, because that's one thing that we're trying to inspect very sort of have a close close discernment on. But this would be the irregularities in the screens themselves could be Kolmogorov turbulence. So that's the second part of the question. The first part about the density contrast is there are two pieces to that. The general part would to just produce the scintillation arc. You don't need a large density contrast, and when I say large, something like even a 1 part in 100, possibly into 1 part in 1,000 can that can give you the kind of the kind of structures that we're seeing. On the other hand, when you see those specific little bright points on the scintillation arc, those things are being bent by presumably by small concentrations of overdensity, and those can be the density contrast could be quite large. And so I didn't do a very good job answering that question, but if the person who asked it follows up with me, I can try to clarify that latter point a little bit better.
Okay, another question. Would you characterize the ISM as appearing more frothy rather than being smooth? So
yes, absolutely. I mean, it seems that it is more bubble-like in the same way that as we learned about the extragalactic galaxy distribution, that is a foam-like kind of distribution as opposed to more continuous. And so, yes, frothy or bubble-like, I think, is a good first description of it.
okay, could separate excuse me could separate scattering densities reflect intervening gas shock waves, or would they be dust clouds?
No, it would be, I mean, something like shock waves is a much better candidate. The dust clouds, we need ionized material here, and so a shock wave would be an example, but we don't expect shock waves every 10 to 20 parsecs along the line of sight, at least naively. Another idea that is being explored by some people is small magnetic domains, like in a supernova remnant, the expanding shell of a supernova remnant. There could be many such small magnetic domains that that the line of sight is piercing through, and there is there's a selection for magnetic domains that are seen nearly edge on. Those can give very enhanced kind of scattering. So that's something that's being explored.
Cool. Another question. Why do we see so many screens in nearby pulsars? Why sources farther away present few isolated arcs instead of continuum? Maybe signal to noise, I'm not sure.
No, not necessarily signal to noise, because there are some distant, very bright pulsars that have been looked at. And what we think is going on there, it's a very good question, but what we think is going on is that by the time you get out to these, beyond these moderate dispersion measures, there are so many of these screens that have been intercepted that it starts to it starts to look just like a uniform scattering near the origin of the secondary spectrum.
Okay. Another question. They said they thank you for your nice talk, but the question is, has anyone looked at these arcs from two different pulsars but located nearly in the same direction? And do we expect to see scintillation arcs that are similar?
Well, that would be very intriguing. The short answer is no. If we had a much more sensitivity than we do have, and we really do need instantaneous sensitivity in order to do this right. I mean, you could imagine, for example, looking at scintillation arcs from a set of pulsars in a globular cluster. And, that would give you distribution, very small angle on the sky, but, but perhaps half a degree or a degree. But other than that, really, nobody has explored that, but it's a nice idea.
Okay. The next question is regarding the clumpiness. Is the observation sensitive to see the same clumpiness in the dispersion measurement variation?
That's a very, very good question, because dispersion measures are monitored very, very accurately in pulsar timing observations. And, we know that there are dispersion measure variations down at the sort of 10 to the -5 level of the dispersion measure. And we can convert that into parsecs per cubic centimeter. But this is we're probing much smaller scales. So if you, let's say that we're talking about a scattering disk of about 10 milliarcseconds across, then at a distance of 1 kiloparsec, that represents just 10 AU in terms of size on the screen. And so that's a much, much smaller sort of inhomogeneity scale than is probed by by measuring dispersion measure over time.
Okay. The next question, we know that the very local interstellar median within 50 parsecs has variable ionization levels because of the large H2 region in the direction of, I think this is supposed to be epsilon and alpha, maybe Cepheus major, CMA. I apologize, I do not know my star abbreviations. Would this affect the scintillation screens? Models show an interstellar ionization gradient in this direction.
It absolutely could, and we definitely, I peeked at some of the who is on the call, saw that Priscilla Frisch is on the call and Carl Heilig.
That's where the questions come from.
Very glad to have both of you listening in, and I well remember the SINS meeting that we attended, the small ionized and neutral structures meeting, and we talked about some of this. And I think there's great need to connect this work to what is known from other studies, particularly about the local interstellar medium on out to the local bubble and beyond.
Okay, and then following up on our previous question, also we know the direction in the local interstellar magnetic field from polarized starlight and the ibex ribbon, which I'm sorry, I'm not familiar with that, but hopefully that means something to you. Does this information enhance understanding of the pulsar scattering screens following?
I think probably not, because of the very different size scales involved. We would be sensitive to magnetic field orientation down at the AU scale, or tens of AU or hundreds of AU scale, and that's probably inaccessible through most other techniques. But still, I mean, knowing about the magnetic structure and magnetic orientation, and particularly magnetic filaments and so on, I think that could be that could definitely be useful information. And I know some people at University of Toronto who are exploring some things like that. So I'd be happy to put people in touch with each other.
Okay, and then we have a non-science question, just asking if you're still at Oberlin and if you had email there, and you'll get those questions in so you can reach out.
I am. I'm actually in the best of all possible worlds from my perspective. I'm retired from teaching, but still active in research, and I will keep my Oberlin email for the foreseeable future. So yes, please contact me through my dan.steinbring@oberlin.edu.
Okay, just any last remaining questions? I'll give it about 10 seconds I can mention, as I'll wait a little bit, and I'll just mention the next community Zoom will be in 2 weeks, where we have Stefano Andrian from Milan talking about, we're switching gears, going out to higher redshift, but also about structure. First massive galaxy clusters emerging from the cosmic web. So frothiness on a very large scale instead of our local ISM. No more questions have come in. So thank you, Dan, very much for your nice talk today. They really neat. And thanks for sharing that meerkat result. I mean,
Oh yeah, no, it's
the signal
astonishing.
noise are spectacular.
No, I know, very exciting. Lots of good work to do with the GBT still, though.
No,
Yeah.
but yeah.
No, great.
Okay, so thank
Okay,
you,
take
Dan,
care.
and thank you,
Thank you, Dave.
everybody.
Okay, bye-bye.
Goodbye.